derivative we use dy over dx, so we call it as y prime, dfx over dx. This is also on the notation, and this is also on the notation. In so many books and so many websites you can find different notations. That is why we are learning about all these notations, and this is the most typical one, and this is also important, and this one, this we use very rarely. Okay, so you have learned about marginal revenue. So idea is the change of the revenue function. So if you are given a revenue function, by taking the derivative you can find marginal revenue. Now let's look at some example. So suppose that an oil company's revenue is given by this equation. So this is the revenue function. Find the function that gives the marginal revenue at any value x. So you need to find marginal revenue. So you need to take the derivative. So first set up the equation, then substitute, then simplify. So you can obtain this one, then take the limit of h to 0, then you can obtain this one. So this is the marginal revenue. And this question in section B, it is asking find the marginal revenue when 20,000 barrels are sold, when x is equal to 20. So you need to substitute 20 for this x, so finally it becomes 660 years. So when 20,000 barrels are sold, marginal revenue is equal to 60. So this is application of the derivative. So basically we use for to find the velocity, to find the marginal revenue, and to find the slope we use this concept. So the second one is tangent to a curve. Especially in geometry, when you are learning or when you are analyzing graphs, one day if you become businessman or engineer, or in other words working in some industry, you have to do some presentations, then there you have to analyze graphs. So you need to find tangent to curve. So this section is very important to learn. So especially in geometry, a tangent to a circle is defined as a line that has one point common in its circle. So this is the circle and this is the line, so this is the one common point, so this is the tangent line. We can draw infinitely many tangent lines for a circle, and for these segments, I mean these line segments also we call secant lines, and from a one point we can draw infinitely many secant lines, but from a one point we can draw only one tangent line. This is the tangent line. Now we are going to find the equation of a tangent line. So this is the derived formula. So the idea in here is this is the difference of fx plus h minus fx, and this is the difference of this independent variable, it is h. When we take the limit to 0, this point comes to here, so the idea is that infinitely many secant lines we can draw from here, but it comes to here, so it becomes a tangent line. So by taking the limit of h to 0, limit of h to 0, we can create a secant line to a tangent line. This is the important one. In any problem, if they ask to find the secant tangent line, you have to use this formula. Let's look at some example, then you can understand. So this is the given problem. Y is equal to f of x, 3 times x square plus 2 times x plus 11. So you need to find the derivative of fx at any point. So using that setup, first use fx plus h minus fx divided by h. So doing these calculations, finally you can obtain this one, and divide by h you can obtain this. Then take the limit of h 0, then it becomes 6 times x plus 2. So finally this is the slope of the tangent line at any point. but in the problem it is asking to find the slope of the tangent line at 1 comma 16. So now you need to substitute the coordinates. As an example, this is the line and this is our point 1 comma 16. So here important one is x coordinate. So now substitute this x coordinate to this one, then you can find the tangent at that point. So after substituting 1 you can obtain 8. So this is the final answer. And for the last section it is asking the equation of the line tangent to this one. So you already know the tangent, it is 8. This is the setup of a typical equation. You have two coordinates 1 comma 16, then substitute to this setup, then you can obtain this as your equation. Okay, so these are the applications of derivatives: velocity, instantaneous rate of change, marginal revenue, slope of the tangent. And differentiability and continuity has a good relationship. As I said you before, it is a step-by-step relation. Here for limits, here for continuity, here for derivative. To discuss without limit, we can't discuss about continuity. Without continuity, we can't discuss about differentiability. So this point is discontinuous, you already know it. And this point is also continuous, but it is not differentiable. The reason is we can draw any unique tangent in here. This point is also not differentiable. The same reason we can't draw any unique tangent. This point is also not differentiable. This is also very important. If a function f is differentiable at point x, then definitely it is continuous at x. But vice versa is not always true. I mean, if it is continuous, we can say about differentiability. As an example, this one. This is continuous but not differentiable. But definitely if a function is differentiable at that point, it is definitely continuous. Okay, thank you everyone. Let's meet on next day.